Good morning, everybody, and welcome again to the CEIA Maths tutorials. Today we've got Trigonometry 1 and 2, and it's going to be delivered by Edmund Collins and Frank O'Keefe. So Ed, I'm going to hand over to you.
Thank you, Eamon, and good morning, everybody. I'm very pleased to be giving you the first part of this tutorial on trigonometry, Trigonometry 1. I gave the first tutorial on which Jerry on indices and logs, and this will be focusing in on trigonometry, which is a topic I'm very fond of. Now, as we've talked about in previous tutorials, the aim here is to go through the principles, the fundamentals of the particular topic, and also do some exam questions. But like the analogy of the toolbox, where you need to be comfortable using different tools to sort a problem, to fix a machine. Likewise, with mathematics, it's very important that you're comfortable with all the tools that you need. So with trigonometry, there are a number of very basic tools. Now, in the second part of the tutorial, Frank is going to go through trigonometric identities, and they're very important in problem solving as well. Now, Eamon has mentioned at the end of previous tutorials the importance of being familiar with your maths and formula tables. And I was looking at the maths tables, the particular section dealing with trigonometry in the last few days preparing for this tutorial. And I did see that a lot of what I'm covering, and probably indeed what Frank is going to cover, is in the tables. But it's one thing knowing, on page 20 that you get a particular formula. It's another thing to understand how it's derived and how to use it and so on. So this is what we're about here. Also then, if you have to become too reliant on the tables, you can lose some time during the exam with going back and forth. So if you're comfortable, you should be able to bypass the tables for some of the particularly frequently used formula and so on. So we'll start the tutorial. Now, the applications of trigonometry are many and varied, and I've just brought a few of them here in the slide. So in this photo of the Canadarm2 on the International Space Station. So the engineers who were designing this arm in Canada, I presume, would have used trigonometry in the design. So that's a very practical application. There you see an astronaut doing a spacewalk around the arm. Another use would be in parallax in astronomy, and you can see there typical triangles and so on. And again, trigonometry would come in there. This is a slide taken from NASA, and you see there I've given recognition to where all these photos came from on this slide. This is a glider trajectory. So this is the glide angle. Has an aircraft is coming in to land, and so on. This is to do with the angle of approach, and this type of calculation is often done on for space vehicle re-entry and so on. It's very important that you get this right when you're coming into the Earth's atmosphere, that this angle will be correct. If any of you have seen that excellent film Hidden Figures, where they talk about that, and the mathematicians who did all those calculations were essential to the success and particularly the safety of the astronauts. So again, another great application of trigonometry. And then the last photo here shows a slide of spherical trigonometry that's used in navigation. So we won't be doing any of that here, but it's another branch, specialized branch of trigonometry. So many are and varied are the applications of trigonometry, but we'll start with some of the basics here and then move on to some more complicated aspects of it. So what I'm going to cover this morning, this part of the tutorial, is measurement of angles, trigonometric ratios, which are commonly known, the basic ones, SOHCAHTOA, reference angles, the signs of sine, cosine, and tangent in the 4 quadrants in a unit circle. This is particularly important that you understand as you move around the unit circle, how the sine, cosine, and tangent change. The sine rule and cosine rule come up quite a bit in problem solving. You'll see some examples later on of where they come in, and then we'll do some exam questions. Hopefully we'll have time to get through a few of them. So measurement of an angle. So the arc length here, S, is r theta on this circle here. But in this case, it's important that thetas and radians. You need to be very careful as well using calculators during the exam that the setting's correct. Some questions, the angles will be in degrees, your answer will be in degrees. Other questions, they may be in radians. So that switching on the calculator is very important. Now we all know that the circumference of a circle is 2 pi r. Therefore, because the arc length is S equals to r theta, that means that 2 pi radians equals 360 degrees. So therefore 1 degree is pi over 180 degrees radians. So 1 radian is equal to 57.296 degrees to 3 decimal places. So just to be comfortable with using degrees and radians, and certainly, you know, using the 2 pi, so start breaking that down. 2 pi is 360, 2 pi radians 360 degrees, pi radians 180, pi over 290, and so on. So that can help with the understanding of degrees and radians. So again, this is what I've just talked about here. This is just a summary of the key angles, if you like, 0 up to 360. So you should be very familiar with those. Now, there are 6 trigonometric ratios that we use, and these are very important to remember. These are for a right-angled triangle. So if you're problem solving, sometimes it's not in the exam questions, it won't be a right-angled triangle, but you may be able to construct a right-angled triangle. And sometimes the problem involves that breaking up a triangle into maybe two right-angled triangles. But these trigonometric ratios we're talking about are all to do with right-angled triangles. And I've used this convention here where this along the x-axis, if you like, is the adjacent, the y-axis here is the opposite, and then as we know, C is the hypotenuse. So we know Pythagoras' theorem, the square and the hypotenuse is equal to the sum of the squares on the other 2 sides. So also with my convention here, notation, the angle opposite the adjacent I've called A, the angle opposite the hypotenuse I've called C, and the angle opposite the opposite, if you like, is called B. So sine of B is the opposite over the hypotenuse. So that's length B over C. And that's called SOH. So we can see here S for the sine, O for the opposite, and H for the hypotenuse. So likewise, the cosine is the adjacent over the hypotenuse. So that's A over C. So again, it's K, so it's C for the cosine, A for the adjacent, and H for the hypotenuse. And then the third one is the tangent, opposite over the adjacent. So that's opposite here, and this is the tan of angle B. All of these we're looking at we're finding the sine, cosine, or the tan of the angle B. So this is opposite over the adjacent, so it's B over A. But you might have noticed as well that the tan is also equal to the sine over the cosine, because if you put the sine, which is opposite over the hypotenuse, over the cosine adjacent over the hypotenuse cancel out, and we're left with the tan opposite over the adjacent. So that can come in handy sometimes in problem solving, to remember that. But they're certainly three key trigonometric ratios. As I mentioned, they're in the maths tables, but really shouldn't, at this level of leaving cert, high level certainly anyway, you shouldn't have to be going to the maths tables to look up these. They should be embedded in your memory, and certainly the SOHCAHTOA TOA can help if you have little difficulty remembering them. So the next three trigonometric ratios, again for the right angle triangle, are really the reverse of what we've been looking at. So here we have the cosecant of the angle, which is the hypotenuse over the opposite. So it's reverse, the C over B. It's 1 over the sine. Sometimes it's difficult, you could get confused. I used to with this, saying, oh, the cosecant is 1 over the cosine. But if you go to the third letter in each of these, S, which is the sine, C cosine, and T for tan there. So certainly these two would help you remember the difference between the cosecant and the secant. Again, secant of angle B is the hypotenuse over adjacent, C over A, 1 over the cosine. And finally, the cotangent is the opposite of the reverse of the tangent, which is the adjacent over the opposite, A over B, 1 over the tangent. So they're the key 6 trigonometric ratios, and particularly the first 3 are ones that are used an awful lot in problem solving. So here's something, I hope you have some pen and paper handy, just based on what we've been doing. I'll just give you a minute. We did this in the first tutorial, some of these questions. So using the information in the triangle above, determine the sine, cosine, and tangent of the 45-degree angle here. Now, obviously, they're both 45 because, as you know, the angles, the total of the 3 angles here in the right angle triangle, this being 90. If one of these is 45, the other is 45. So this is obviously this is good information to have, because you may want to know both, but certainly for 2 45s here and 90. So I'll just give you a minute there to work out the sine, cosine, and tangent of a 45-degree angle. And our sine is opposite over the hypotenuse, cosine adjacent over hypotenuse, and then the tan opposite over the adjacent. So here we have the final results. So we can see from Pythagoras' theorem that if we have 2 sides length of 1, that the hypotenuse is going to be the square root of 2. And therefore the sine is going to be 1 over square root of 2. The cosine is the same in this case, 1 over the square root of 2, and the tan is 1 over 1, which is 1. So they would be fairly standard results, and again, pretty sure they're in the maths tables, but you should have some of these in your memory. And also when you get down to the likes of 30 degrees, 60 degrees. These would be standard type given in this sort format. Now, we're going to go through reference angles here. They're very important because while often it'd be nice just to be dealing with angles, acute angles less than 90 degrees. Often in problems we don't have that. We can be dealing with greater than 90, greater than 180, and in fact multiples of 360 as well. But you'll see later on how this is a repeating pattern, if you like. If you understand how things operate within 360 degrees or 2 pi radians, then you will be able to transfer that on into the multiples of 360. So the reference angles are used to determine the sine, cosine, and tangent of angles which are greater than 90 degrees. We've already been through the angles less than 90 degrees situations with standard for the right angle triangle. We've been through that. If angle A is less than the 90 degrees, which we've been looking at, then the reference angle is itself. So that's straightforward enough. But what happens if the angle in this case here is greater than 90 but less than 180? So what you do is you move in this direction. So you move counterclockwise. You're always working counterclockwise in this business for these reference angles. So what you do is you drop a line here, the circumference down to the minus x-axis, and you trap this angle here between the x-axis and the radius here. So this is the reference angle here, or. So the reference angle then becomes 180 degrees minus the angle itself minus A, which you're looking for. So in this case, the reference angle is in the second quadrant. We call this is the quadrant going anti-clockwise: first quadrant, second, third, and fourth. So again, we could be looking at a situation where the angle is greater than 180 degrees, but less than 270 degrees. So we're in the third quadrant here. Again, we bring the line up here to the x-axis, and we trap this angle here between the x-axis and the radius. This is, in this case, it's the reference angle is a minus 180 degrees in the third quadrant. So we've moved into the fourth quadrant now. Quite a big angle here. It's less than 360, but greater than 270. So again, bringing this line up here to the x-axis, trapping the angle here. This is our reference angle here. So in this case, the reference angle is 360 degrees minus A in the fourth quadrant. So we can see here we're working in the first quadrant, the unit circle here. And it's important to not only know how to calculate the reference angles in the different quadrants, but what the sign is going to be. If you use the ones here, it's the signs of the sine, cosine, and tangent in the different quadrants. Because you could end up in trouble if you don't calculate them out correctly. You get an error in your calculations. So looking at our first quadrant here, everything is straightforward. So we have the sine, cosine, and tan are all positive in the first quadrant, because the reference angle is the angle itself, and everything is positive here. I've just put here some typical angles here. So if the angle is 0, the sine is 0. Because obviously if you think of the radius coming back down onto the x-axis, remember the sine of the angle is the opposite over the hypotenuse. So this is going down here. This length here is going to 0. So it's 0 over the hypotenuse. So that's why it's 0 here. However, in this case, the cosine is 1. Tangent similarly is 0. If the angle's 90, the sine is 1. The cosine is 0. The tangent is undefinable because you're dividing by 0. That's why, and you'll see this in another representation, which I find somewhat easier to understand than the unit circle, but the unit circle is given in a lot of the textbooks. So we're in the second quadrant now, and in this case, the sine is positive again, because this is the positive y-axis. The hypotenuse is neutral, if you like. The cosine, however, is negative because we're talking about this, the negative x-axis, and the tangent is also negative in this case. So in this case, the angle 180 degrees. The sine is 0, cosine is -1, and tangent is 0. Into the third quadrant, the sine of the angle is negative again. The cosine is -2, but because both the sine and the cosine are negative, remember back to the tan being sine over cosine, the tangent is positive. For the angle, the extreme angle of 270 degrees, the sine is -1, the cosine is 0, and the tangent is undefinable again. And finally, in the fourth quadrant, the sine is negative again. Here you can see from this sine of the reference angle will be negative. The cosine is positive here, because there is the positive axis here, and the tangent again is negative. And again, for 360 degrees, sine is 0, cosine is 1, tangent is 0. Now, there's a lot to take in there, but there is an easy way to remember it, and that is using this acronym ACTS, ACTS. In this case, however, it's going in a clockwise direction, starting with the first quadrant here. So the A means that all the sine, cosine, and tan are positive. In the fourth quadrant here, it means that the cosine is positive. In the third quadrant, only the tan is positive, and then in the second quadrant, only the sine is positive. So that's, if you were in the exam and you're doing something in relation to this, angles greater than 90, you could draw this out, and it would help you because you could be working in this quadrant here. So ACTS is an easy way to remember all of what we're talking about. But there is another way that you could see it. As I say, we'll be looking at that view now in a little while. And here it is. So this is a graph of the sine and cosine. And as I say, I like thinking in this way. So in the blue here, you have the sine, and in the red, you have the cosine. So this summarizes what we've been talking about here. So the period here is 2 pi, and then you can see the pattern repeats itself here. So it goes from 0 to pi to 2 pi. So likewise for cosine, they're out of phase here. You can see that they're actually 90 degrees out of phase, which is very interesting. You pick up a lot from this. You can also pick up, negative angles here, which is going in the opposite direction, the clockwise direction around the unit circle. So what the value is for them. So you can see that it reaches a maximum here of 1. So you'll never go beyond. If you're doing some calculations and you're getting a value for sine greater than 1, something's gone wrong, or indeed for cosine. So Another way, this is really what we've been looking at on the unit circle, but displayed in graphical format. It does go here to -1, I say as well. So sorry, should have said that it's either 1 or -1. So we saw that earlier. So in the case of pi, the sign is -1. So a good view of how the sine and cosine operate and the phase difference between the two, and what happens then when you start repeating the cycle again, the period again, going from 2 pi, 3 pi up to 4 pi, and so on. It just keeps repeating indefinitely. So a good view there. This is similar. It's graph again for period not to 2 pi and so on, but and not to -2 pi. But in this case, it's the tan of the angle, and you can see as you approach pi here, this becomes undefinable here. So because you're dividing by 0. But again, this is repeating the tan of 0 is 0, and tan of pi is 0, and so on. So again, the period here can be seen, and how it repeats. So a good way of viewing sine, cosine, and tan, but the tan is very different graph, obviously, to the sine, cosine. So based on what we've just been doing there in terms of reference angles and unit circle and so on, you might try this little question here. So find the sine, cosine, and tangent of 135 degrees. So I'll just give you a minute to work on that. Remember, 135, it's greater than 90, less than 180, so we're in the second quadrant. And to find the angle, 180 minus 135. So here we are. So the reference angle in this case, 180 minus 135 is 45. Sine of the 45 in second quadrant is 1 over √2. So we know that that's positive because from the axis ACTS, sine in the second quadrant is positive. However, the cosine and the tan in the second quadrant would be both negative. So because we've seen before, sine and cosine have the same value but different signs. So the cosine of 45 in the second quadrant is minus 1 over √2. And then we can see here the tangent of 45 in the second quadrant is -1. Now, we'll come on to the sine rule. Again, it's in your maths tables, is used quite a bit in problem solving. So it's quite a simple rule to remember. So it's A over sine A, which is the sine of the angle opposite this length A, equals B over sine B, equals C over sine C. Or it can be reversed and written this way as sine A over A equals sine B over B equals sine C over C. Now, there's a few things to remember about using the sine rule. It's used for non-right angled triangles. That's the first thing. And very importantly, it's used when you know the length of one side and the angle opposite it. So that's very important, the length of one side and the angle opposite it. And you'll see, hopefully, in some of the questions here, how that works out. So often in a question, you're given trigonometry, you're given an angle, you're given the length of a side, two sides maybe. So the first thing is to write down what you've got and to determine what you can find from that information and what rule to use. So it's quite logical that way, and there's only a few options: sine rule, cosine rule, if it's a right angle triangle, SOHCAHTOA. So it's quite limited, so you don't have an awful lot of options. So you can move along through the problem quite quickly once you've decided what tools you're going to use. Now the cosine rule, a little bit more complicated. Again, it's in the maths tables, but if you can remember how it's constructed, that will help you. In this case, a squared, this length here, equals b squared plus c squared minus 2bc, the cosine of a. So that's why it's called the cosine rule. Previous one, you only use sines, this is using cosines. But you'll see here, one way to remember here is that this a here, and if this a here, so it's this angle opposite here. So and then b and c here, we see here. In the previous version of maths, you probably would have been asked to, before project maths, derive the formula for the cosine rule, but that isn't done anymore, so you don't have to worry about that. But if you did want, there would be in your textbooks the derivation of that, just to understand how it comes about. It's not too complicated if you want to work through it. But another version of the cosine rule is a bit like with the way the sine rule works. You have this, in this case, b squared equals c squared plus a squared minus 2ca, the cos of b, and then finally c squared equals a squared plus b squared minus 2ab, the cos of c. Really the important thing here in using this rule here is to remember here that this angle, if you're dealing with the c here, that it's opposite the length c. Or if you're dealing with a, it's the angle opposite the length a. Used for again non-right angle triangles, and used when you know the length of sides but not angles opposite them. So if you're given some lengths here, and you having the angles opposite, then you can actually use that to work out the cosine of a, and in turn work out what the angle a is, and likewise move along and work out b and c if needs be. So I hope that's given you some good idea of the fundamentals and the principles behind trigonometry. As I say, not many things to consider. So the rules are and theorems and so on are relatively small in number, but very important. So you're going to be certainly, you can be sure that trigonometry is going to come up in questions on the Leaving Cert in one way or the other. It may be part of questions, and in one of these it wasn't the full question. In another it is the full question. So I've picked out some examples here, and I would certainly recommend, like any of the other topics, practice is key. The more questions you can do, the better. The Leaving Cert papers are all available online, and the marking schemes as well. But please, work it out first. Don't try and go to the marking scheme and the question, have both together and try to see how how the solution came about, you won't really learn that way. If you're really stuck and you can't get through it, well then go to it and see how it's worked out. But the key is to develop your own problem solving skills, and that is by practice. Just the more you practice, the better you'll get, and that's for sure. So these are some examples. They're really a lot more available. I've just picked out these for the tutorial, which goes through some of the principles that we've already covered. And I probably won't today do this question. It's quite a long question from 2016, but I'd recommend that you actually attempt it in the next week or so following the tutorial, because it brings together quite a lot of what we've been talking about, but just because of time constraints, I probably won't get to that one. But we'll start with a fairly recent one, which was part of a question on 2020. So I'm just going to switch over to my pad here, and I'll be able to bring up the paper and to go through the question. Is that visible, Jerry? Or sorry, Eamon?
It is, Ed.
Sorry,
no problem.
Yeah. Thanks. Now, this is question 8 from 2020, and I'll be going through two parts. Part A, 1 and 2, which are directly related to trigonometry, but trigonometry comes up in subsequent parts of the question to some degree. So you can see here that we have a rectangle is inscribed in a circle of radius 5 units. So this should be familiar to looks what we were working with in the unit circle there. So we have radius 5 units. The center O is at 0, 0. So you should be familiar with this terminology. This is 0x, 0y here. And let R be denoted by this xy. So those are the coordinates of R here, xy. Where x and y, and again, you should be all familiar. We talked about this in the first tutorial. X and y are real numbers here. That's what this means. So that's this point here. That's the vertex of the rectangle in the first quadrant. So this is this terminology here. First quadrant here we're dealing with. This is the angle here, theta. The angle between OR and the positive x-axis here, where again you can read this 0 less than or equal to, or sorry, theta's greater than or equal to 0, but less than or equal to pi over 2. So you should be familiar with all this terminology. You should be able to read it like with the English here. And sometimes with this, I like to read it this way, looking at the theta, the greater than here, and then the less than here. That's one way of reading it. So basically what we're saying here, look, that theta's in the first quadrant less than 90 degrees. But again, you see here, they're using the radian notation. So that's why it's important to be able to switch between degrees and radians. So first part of the question, the point Rxy can be written in a different format, and this is often used for denoting the coordinates on a circle, where it's written as A cos theta, comma B sine theta, again where A and B are real numbers. So the question is, find the value of A and the value of B. So this is a very easy question actually, because it just goes through what we've already been talking about. So if we go through, so we'll start with the cos of theta equal to x over 5, and the sine of theta equals y over 5. So then we can write it this way, that x equals 5 cos theta and y equals 5 sine theta. So because we want to get it in the notation of a cos theta and b sine theta, it'll be 5 cos theta, 5 sine theta. So in this case, a equals 5 and b also equals 5. Now that might throw you a bit, because when you're doing that question, you might think that they're going to be different, but in fact they aren't. So a equals 5 and b equals 5. So very simple question in a way, but you know, once you know your SOHCAHTOA and so on, and you're familiar with the terminology, it's quite an easy question to do. The next one is built on the first question. You often find that you know, you work through one part and then the second part will use data that you found in the first part, and this is the case here. So show that the area, so they're giving the area in terms of theta. So again, terminology might be a little strange, but it's the area, it's like a function. So you want to show it in terms of theta. The area of the rectangle measured in square units can be written as the area in terms of theta equals 50 sine 2 theta. Now I like these questions because they give you the answer, so that helps. At least you know whether you're right or not in the end. So looking back at our rectangle here, we've already calculated x here, and we've calculated y. But to calculate the area of the rectangle, it's going to be this length here by this length here. But we can see here that this length is going to be 2x, this length is going to be 2y. So our total area here is going to be 2x multiplied by 2y. So that's good, because we already know that x is 5 cos theta. So 2x is going to be 10 cos theta, and 2y is going to be 10 sine theta. So we can write that down there for a in terms of theta equals 10 cos theta by 10 sine theta. That equals 100 cos theta sine theta. Now, Frank is going to cover the identities later, and I think one of the ones he covers is 2 cos theta sine theta, and 2 cos theta sine theta is equal to sine 2 theta. So we can rewrite this as 50 times 2 cos theta sine theta. And that equals to 50 times sine 2 theta. So that's it. The first part of the question done. Quite easy, really, if you're familiar with all the relevant information or tools that you need to solve it. So that's the first question. You might look at the other parts as well. There's differentiation comes in there. It was an interesting question. They mixed that in with the question. So this is the point with the mathematics. You need to be familiar with different aspects to work on questions, because you're going to have different topics mixed in to the one question. Okay, that's the first question. Now, this second question isn't as easy, but a lot of what we've been looking at comes up in this question. So it's back from 2019, paper 2, question 9. So is that visible, Eamon? Yeah.
It is, Ed. Yeah.
Thanks. So interesting problem here. We obviously haven't got a right angle triangle. So we do have a triangular patch of ground with the triangle SGH here. And as I mentioned earlier, they're going to give you some information. So in this case, they've given us length SH is 58 meters and length GH is 30 meters. And they've also given us an angle. And this is the way they denote the angle here, GHS is 68 degrees. It's a helicopter pad. And then they're giving us a point P, which is inside the circle, which is inside the triangle. So they're obviously touching the circle's touching the sides here. So the first part of the question here, they want us to find this other side here, SG. They want the answer in meters. That's important to obviously remember your units, and also look at the decimal places. You could drop maybe it's very small number of marks, but you could just drop something if you didn't have it to the correct decimal place. So please read the detail, meters, decimal places here. So straight away here, we're seeing, oh, look, it's going to be a sine rule or a cosine rule to solve this problem. And in fact, if you go back to the rules about applying sine and cosine, it's actually the cosine rule here, because we have two sides. We have two sides and an angle, but we have this side here, which is opposite the angle here that we're looking for. So that's the key here. So remember, from the cosine rule, it's in this format, but we're going to write it out in this way. All right. So SG squared equals 30 squared plus 58 squared minus 2 by 30 by 58 by the cosine at 68 degrees. So there's a little bit of working out, just doing the calculations, but again, with your calculator here, you're working in degrees, not radians, so that's straightforward enough. Calculate this out, and it should work out to 2960.369. So therefore, SG equals 54.4 meters. I always like to write the units after. And again, remember, we're dealing with one decimal place here. So be familiar with your decimal places here. So it only wants it to 1, so 54.4 meters. So the next part, again, say you're using what you've already found, the information to find to find the solution, the next part of the question. And in this case here, they're looking for the angle HSG. So this angle in here we're looking for, but they wanted 2 decimal places in this case. So what can we do here? So so we have the side opposite the angle we're looking for, and we know from the sine rule, therefore, that we once we have that side, we have the side over the angle equals another side over an angle. So we already have calculated SG here. We know this angle here, so straight away that points us to the use of the sine rule in this case. So what we can say then is 54.4 over the sine of 68 degrees equals 30 over the sine of the angle HSG. And you then be able to reverse this, so that's sine 68 degrees over 54.4 equals the sine of HSG over 30, and we can work out that the sine of HSG is equal to 0.51131. And using your calculator, you find what angle has a sine of 0.51131. And the angle is, remember now we're working to 2 decimal places, is 30.75 degrees. Working in degrees here, no radians, so straightforward enough here. So that's the first 2 parts. Interesting, using the cosine and the sine rule. So the next part, C, then asks you to find the area of the triangle SGH, which we've been working on. in meters squared and correct to 2 decimal places. Now, there's a number of ways you can find the area of a triangle. You can use the standard formula half the base by the perpendicular height if you know it, or else in your maths tables you're given the formula half AB by sine alpha, or the equivalent. So that's the one we're going to use here, and because we know that this angle is 68 degrees. We have this length here 30 with this length here 58. So it's quite straightforward then to calculate the area of the triangle has been half by 30 by 58 by the sine of 68 degrees. And that works out at 806.65 meters squared to 2 decimal places. So again, something you'd be familiar with from your tables, that formula for the area of the triangle. Just pick the right one on the right sides and the angle, and you have that quite quickly. The next part of the question talks about finding the area of the triangle HSP in terms of R, where R is the radius of the helicopter pad. So what we're talking about here is this triangle here, so HSP, and this is where you can use the other formula for calculating the area of a triangle being half the base by the perpendicular height. We know the perpendicular height. This is perpendicular here as R, 90 degrees here. So half the base, half of 58, multiplied by the perpendicular height, which is R. So it's straightforward enough. So the area is half of 58 by R, which is 29 R. So that's I think that's as far as I'm going to go with this, because I think I've shown how we can use the sine cosine rule and the two formulas for the area of triangles to help solve that problem. I would suggest you keep working through this. It's actually quite easy. Apart the last part is a little tricky, but these two parts, part 2 and 3 of D, are straightforward enough, and then the last part, part E, a little tricky, but you use the tan there, so that'll help solve that problem. So please try that in the next few days while the tutorial is still fresh in your mind, and I wish you the best of luck with trigonometry, and all your other topics in mathematics. And thanks for your attention.
So welcome back, everybody, to part 2 of the Trigonometry 1 and 2 tutorial today. Next up, we have Frank O'Keefe, who's going to take you for part 2 of the tutorial. So I'll hand over to you, Frank. Is that okay?
Okay, let's get started. So, okay, my name is Frank O'Keefe. I'll be doing the second half of the trig tutorial. So let's get started. So I'm going to be covering the following topics: the trig functions using negative angles and complementary angles, compound angle formulae, then double and half angle formulae, and then the sum, difference, and products formulas. All of these you'll find in your log tables. It's useful to know how to derive them, or at least know where they come from. Some of those derivations are potentially examinable. And then we'll move on to some problems. Typically, trig identities are commonly asked. And finally, I'll do some more examples and exam questions. Okay, so let's get started on that. Let's look at the sine, cos, and tan formula for negative angles. So let's start just to remind you, for positive angles, if you look at an angle drawn in a unit circle, a positive angle is one that's considered to be one that's anti-clockwise, starting from the x-axis. So starting from this point, if you rotate anti-clockwise an angle A, that's considered to be a positive angle. And in that case, the you can look at the intersect point up here and its coordinates, which we call x and y. Its coordinates are the cosine and the sine of the angle. You can see that from the fact that the adjacent to angle A is the distance horizontally, which is the x coordinate, and the vertical distance from the x-axis is opposite to the angle, and that's the y coordinate. Okay, so for a positive angle, it's simple. The cosine is equal to w, which is the x coordinate. The sine is equal to h, the height, which is the y coordinate. So what do we mean by a negative angle then? We mean one that's clockwise from the x-axis. So I've drawn in the negative angle minus a here, rotated clockwise from this x-axis. And it's a similar situation. There's the opposite to the angle is this distance h, and the adjacent is the distance w. Now the adjacent is still in the same direction. The opposite h is now going down below the axis. So the y coordinate, y2 here, is negative. It's minus h. So the cosine then is the same as it was for the positive angle, but the sine is minus h, so it's the negative version. It's negative compared to the sine of the positive angle. And so these are the equations here. The cosine of minus a is the same as the cosine of a, but the sine of minus a is minus the sine of a. Right, finally, if you want the tan of a negative angle, use the fact that a tan is defined to be a sine over the cosine. So the sine, take the sine and the cosine of those negative angles. You see that the numerator, the sine, changes sign. The cosine stays positive or stays the same sign as it was. And you end up with the overall tan becoming the negative of the original tan. And that brings us to the 3 formula here for cosine, sine, and tan of the negative angles. The cosine remains unchanged. The sine and the tan have inverse signs on them. Just flipping towards the log tables. I have an old version of log tables here, and those 3 equations are down here at the start. Okay, so those are negative angles. What about complementary angles? Complementary angles are ones that add up to 90 degrees. So if you look at a right-angled triangle, if an angle A is on one side of it, then the opposite, the non-right angle opposite, is the complementary angle B, and the two of them obviously add up to 90 degrees. And what you can see from the triangle is that this y value here, which is the opposite of the angle A, is adjacent to angle B. And so this means that because they share the same hypotenuse, the sine of A, which is y over z, y over z, corresponds to the cosine of B, which is y over z again. Similarly, x here is adjacent to the angle A, but is opposite to the angle B. So the cosine of A is equal to the sine of B. And these are summarized down here, that the sine of the complementary angle to A is equal to cosine of A, and the cosine of the complementary angle of A is equal to the sine of A. And in the case of tan, you invert it because you're replacing the opposite and adjacent. And the way of looking at this is to, if you want to swap between an angle and its complementary angle, you swap the sine and cosine, and you invert the tan. Okay, inverse trig functions. You can look at a trig function, sine, cosine, or tan, as taking an angle and working out a ratio, a number that corresponds to that angle. The inverse of those functions goes the other way, and it gives you the ratio, gives you a number, and asks you to produce the angle which would have that ratio. So for example, the inverse sine of minus 0.5 is the angle that has a sine of minus 0.5. And that works for cosine and tan. So you have an inverse sine, inverse cosine, and inverse tan. They're sometimes called arc sine, arc cosine, and arc tan, if you hear those terms. So let's look at the case I mentioned there. What angle has a sine of minus 0.5, which is working out the inverse sine of minus 0.5. If you remember from what we said before, when we draw an angle on the unit circle, the y value corresponds to the sine of the angle. So if you have a y value, a sine of minus 0.5, that corresponds to a y value of minus 0.5, which is everything along this line. But we're restricted to unit circle, so it's where this line intersects the unit circle. And you can see that it intersects at 2 points. At this point here, which is the angle minus 30, but also over at this point, which is the angle minus 150. So there are at least 2 angles that give you a sine of minus 0.5. And in fact, there are more than that, because if you were to rotate this angle around by 360 degrees, it would bring you back to where you were. So if you add 360 degrees onto this angle, you end up with another angle that still has a sine of minus 0.5. And similarly, you could rotate this one around 360 degrees and get back to where you were and still have the same sine. We can illustrate that by looking at a plot of the sine function. It's periodic and repeats every 360 degrees, as Ed showed before. So the angles that we had before, the minus 150 degrees, had a sine of minus 0.5, and minus 30 degrees also had a sine of minus 0.5. But if we carry on another 360 degrees to the angle 210 degrees, which is 360 more than minus 150, we get back to a point where the sine is minus 0.5 again. And if we keep going so that we're 360 degrees beyond minus 30, which is 330, again, we're back to minus 0.5 for the sine. And you can add another 360 degrees again, and so on, and you keep returning to a sine of minus 0.5. So there are an infinite number of angles that have a sine of minus 0.5. Now, if you're asked the question though, well, what is the inverse sine of minus 0.5? You need a convention to pick out one of those, because if you enter it in your pocket calculator, you'll get one angle back. And the convention is that for sine and tan, you use the angles that are between minus 90 and plus 90 degrees. So in that case, it's between here and here, which would be the angle minus 30 degrees. And that's what your pocket calculator would return. For inverse cosine, the convention is between 0 and 180 degrees, so in this range here. But there will always be another angle, or at least usually will be at least one more angle on the unit circle that has the same value of sine or cosine or tan. And you need to do that by inspection. Just look at the unit circle and see, what is the other value there? In what quadrant will you see that second solution? And then you can find more solutions by adding any multiple of 360 degrees to those two solutions that you see on the unit circle. And we actually see an example of that in an exam question later on. Right, compound angle formulae. If you look back at the log tables, you'll find these compound angle formulae. They're useful. You don't necessarily need to remember them. You need to remember that they exist and where to find them. If you do enough trigonometry, though, they'll become second nature and you will remember them. Now, we'd like to see how to derive this, and the derivation of these is, as far as I know, required to be known in the Leaving Cert course. So the conventional way of deriving them is to derive this one first, and then it becomes easy to convert that to these other three. So we start by trying to derive this cosine A minus B in terms of the other simpler angle. Right, so let's try to work out a formula for the cosine of A minus B. Let's start off with an angle A, whose x and y coordinates on the unit circle are cosine A and sine A. Then we look at another angle B on the unit circle. We choose a smaller one so that A minus B will be a nice positive angle. And then we combine the two in the same diagram. And we see that we've got this angle A minus B between those two line segments here on the unit circle. And it's a unit circle, so this triangle that we've now formed has two sides of unit length and one side of different length, which we call L. And you can probably spot immediately that this triangle here, we can apply the cosine rule to it to work out the cosine of A minus B. So let's try that. If we work out the cosine of A minus B using the cosine rule, there's an unknown L in it. So we need another way of working out L, but we know the coordinates of these 2 points, 2 endpoints. So we can use the formula from coordinate geometry for the distance between 2 points, which is effectively the Pythagoras formula, to work out L in another way, or in fact, it's convenient to work out L squared rather than L, because L squared occurs in the cosine rule. So using these two ways of calculating L, we can then eliminate L, and we're left with a formula for cosine of A minus B. That's a general strategy. Let's go through the details of that. The cosine rule for this triangle, well, the L squared is equal to this one side squared plus another side squared plus 2 times the sides multiplied times the cosine. For the Pythagoras formula from coordinate geometry, for the distance between those 2 points, it's x2 minus x1 squared plus y2 minus y1 squared. And we can replace the x2, x1 by the cosines and the y values by the sines. And now we have everything in terms of the sines and cosines of the single angles. So let's proceed with that. And let's take the second formula first. This is the Pythagoras formula for the line segment length. We get the cos minus cos squared and the sine minus sine squared. Just need to multiply them out. And then a common trick in trigonometry is to look for a cosine squared plus a sine squared of the same angle, because we know that cosine squared plus sine squared add up to 1. So we see this term here, we group them together. We also have a cosine squared b and a sine squared b. We group them together, and we leave the other terms as they are. And now we can replace this cosine squared plus sine squared by 1. We can replace this cosine squared and sine squared by 1, and leave the other terms and add those ones together. We got this. And you can see there's a common factor of 2 in all these terms, so we can divide across by 2. And we had L squared, so it's L squared over 2 is equal to all of this divided by 2. So keep that aside for a second, and now we'll go back to the cosine rule. And we try to arrange it so that we get a cosine of A minus B. So rearranging the cosine rule formula here, simplifying, and dividing by 2, we end up with a cosine A minus B is 1 minus L squared over 2. But we have L squared over 2 worked out in terms of the single angle functions, like here, which we can substitute, replace this L squared over 2 by this here. The ones cancel out, these signs invert, and we end up with the desired result, cos A cos B plus sin A sin B. And that is the formula we were trying to prove. Okay, now the other 3 compound angle formulas. The first one, we're looking for the positive version, the sum angle instead of the difference angle. And you can see that to get this formula, we just replace the minus b by plus b, or equivalently replacing b by minus b in the original formula. And that gives us cosine of a plus b. But now the cosine, the b in the original formula gets replaced by minus b. And we use the fact that the cosine of minus b is the same as cosine of b, but the sine of minus b is minus the sine of b. So that this becomes this cos A cos B minus sin A sin B. How about the sign of the sum? If you remember from before, to swap between sines and cosines, we just use the complementary angle. So the sine of one angle is equal to the cosine of the complementary angle. So we're looking for the sine of A plus B. We work out then the cosine of 90 degrees minus the angle A plus B. And rearranging that, it works out to be the cosine of 90 minus A minus B. And now we've got the cosine of the difference between two angles, which we have the formula for. It's cos one angle by the cos of the other plus sine of the first angle by the sine of the other. But now the first angle is the complementary angle of A rather than A itself. And again, remember, the cosine of a complementary angle is equal to the sine of the angle. And the sine of the complementary angle is equal to cosine of the angle. So make that final substitution, and we end up with sine A cos B plus cos A sine B. And last of all, then, the sine of A minus B, we're replacing in the original formula, we just replaced B by minus B. And again, note that the cosine of minus B is the cosine of B. The sine of minus B is minus the sine of B, which gives us that final formula. And just grouping them together then, well, I haven't grouped them together. Those four results are grouped together here in the log tables. So you should know that they exist and know where to find them in the log tables. Now, what about the tan of some angles and the tan of different angles? Well, you just use those two previous results for the sine of A plus B and cosine of A plus B. Noting the tan of A plus B is defined to be the sine of A plus B over the cosine of A plus B. And you will get, well, straight substitution of those values in here. Now, in this case, now you've got to decide how to proceed from here. And in a case like this, it's generally a good idea to look at the result you're looking for. The result you're looking for is this, and you'll notice that there is a 1 in this first term underneath the line. So you ask yourself, how will you get a 1 down here? And the answer is to divide this by cos A cos B. But if you do that, you will get the 1, but you need to divide every other term, top and bottom, by the same amount, by the same factor, in order not to change the value. And when you do that, you get the 1 that you hope for. On the top here, you find that the cosine B's cancel, and you're left with a sine A over cos A, which is a tan A. For the second term, the cos A's cancel. You're left with a sine B over cosine B. And for this second term underneath the line, you don't get any cancellation, but you have a sine A over cosine A and a sine B over cosine B, which works out to be tan A times tan B. And that gives you the results you were looking for. You can replace, for the tan A minus B, you're just replacing the plus B by the minus B, and noting that the tan of minus B is equal to minus the tan of B. And it gives you this corresponding formula for the tans, for the tan of the difference angles. Okay, so those are the compound angle formula. The double angle formula then are a simplified version of the compound angle formula, where you just put B equals A. And for the cosine of A plus B, it becomes cosine of 2A. Just replace B by A in the formula. You get cos A minus sine A, which is cos squared A minus sine squared A. And that is one way of expressing cos 2A. Now, if you want, you can express it just in terms of the sine of A by saying that cos squared plus sine squared is equal to 1. So cos squared is equal to 1 minus sine squared. And that gives you 1 minus 2 sine squared A. Alternatively, we could have replaced sine squared by 1 minus cos squared, and we would have ended up with a slightly different expression of 2 2 cos squared A minus 1. And you can play other tricks and express it in terms of tan A as well. So this cos 2A can be expressed in many different forms, and that does get asked in questions of proving that it can be shown in these different forms. In the log tables, it shows you, here's one form that we saw. Here's another form. And if you think about it, this can be arranged as a cos 2A equals something as well. And there are 2 other forms of cos 2A. So there are many ways of expressing cos 2A, and you should get used to making those substitutions, because it does come up in a lot of questions. For the sine 2A, it's a bit simpler. It's just replace B by A in the compound angle formula, and you get 2 sine A cosine A. There's not much you can do with that. Tan 2A, similarly, you replace B by A in the tan A plus B formula, and you get 2 tan A over 1 minus tan squared A. Now, there are half angle formula you can work out as well. These I don't think are in the log tables, at least not in my old version of the log tables. But you simply just substitute, replace the 2A in the double angle formula, replace that by, say, X, and you can just have an equivalent half angle formula by replacing 2A by X, and then A becomes X over 2. It's useful to know that you can do that, even if it's not in the log tables. And we'll see later on how that can be used in a question. Now, there are these other, I'll just go back to the log tables here. There are these other more complicated looking formulas. They're called products of sums and differences, and sums and differences of products. These I wouldn't say you need to remember, but remember that they exist. If you did need to derive them, I've never seen that asked, but if you did, the products of sums and differences are simply got by adding and subtracting the original compound angle formulae. So, for example, if you add 6 and 7, these 2 terms cancel out, and you get 2 sine A cos B, and so on. By subtracting them, these 2 terms cancel out, and so on, and you get these 4 formulae by adding and subtracting these original ones selectively. For the sums and differences of products, it's a little bit more difficult to do that. You need to substitute A plus B over 2 for A, and A minus B over 2 for B. And that way, when you add them, you get A, and when you subtract them, you get B. You can convert this formula to this formula with that substitution. I've never seen that asked, but it is in the log tables, so they might potentially ask you to do that. But it's probably just enough just to know that these formula exist and are available in your log tables in case it does come up in a problem. Okay, so now let's move on to the problems involving these things that we've just covered. And one class of problems is trigonometric identities. That's where you try to show that one expression is equal to another. So, for example, cos 2A is equal to cos squared A minus sine squared A is one identity. That's one that is in your log tables. Let's flip back to the log tables here. Here it is up here. But you might be asked to show an equivalent identity. So for this one, the cos 2a being 1 minus tan squared a over 1 plus tan squared a. The question is, how do you get from this to this? And with the trig identities, there's always a little bit of trial and error just to get started. You have to ask yourself, how would I get to this? How would I get to this from this? And one clue is that you've got tans in the result you're looking for. And to get to a tan, you need to divide a sine by a cosine. So if you look at this term in the original equation, you can say, well, to get to a tan squared, I might need to divide by a cosine squared here. So how would you do that? And a common trick in trig identities is to convert between cosine squared plus sine squared and 1. And that's the trick you need to do in this case. So you start with your original formula for cos 2a. You write it as itself over 1, and then replace the 1 by cos squared plus sine squared. And then you divide above and below by cosine squared in order to get the ones here that you were looking for. And when you do that, you also get the sine squared over cos squared on this side, which is the tan squared you were looking for. And yeah, and that's your answer then, 1 minus tan squared over 1 plus tan squared. And you need a little bit of practice and intuition to know how to go about these trig identities. So let's go through a few more of those just to illustrate the process. Right, here's a typical question where you're asked to show that one term equals another. And the general strategy is to start with the left-hand side and see how you can manipulate it into something that looks like the right-hand side. In this case, you can see that the left-hand side contains functions of 2a, but the right-hand side, which you're trying to end up with, only has a function of a in it. So that's a clue that you should try to replace the function of 2a with a function of a, or functions of a. So this is where these cos 2a double angle formulas come in. One expression that we worked out before is that it's equal to 1 minus 2 sine squared a. Now, if you were to replace that cos 2a above and below, you'd end up with sine squared a above and below, and that doesn't get you where you want to go. To get to a tan squared, you really need sines on top of the line and cosines underneath the line to get tans. So we'd like to replace the cosine above the line here with something that contains sines, which is this formula. But we'd like to replace the cosine underneath the line with something that contains cosines of the single angle. So we manipulate this angle, this formula, using the trick of sine squared is 1 minus cosine squared, and we get it in this form, which contains only cosines. And then we can see that when we've done that, we've got sines of the single angle above the line, cosines of single angle below the line. Rearranging these two ones cancel out, and those two ones cancel out, and you get your sine squared over cosine squared, which is the tan squared you were looking with. Now, this may not have been obvious to take that route, and unfortunately, with these trig identities, you do need to think about it for a while and might be a little bit of trial and error to get you on the right track. But once you've done a few of them, you start to develop an intuition as to the right way to go about them. Let's do a couple more of these. So if you're asked to show that sine x over 1 plus cosine x is the tan of x over 2. Well, we're looking for a result that has the half angle in it. So we want to replace our whole angles with half angles using the half angle formula that we worked out before. It seems like a logical way to go. So we use the half angle formula for sine x, which is this one, and the half angle formula for cosine x, which is this one. And when we do that, we see that we've got a cosine x over 2 above and below the line, which we can cancel out. We're left with the sine x over 2 over cosine x over 2, which is the tan x over 2. Now you could have done it this way. If you didn't remember the half angle formula, you could do it slightly differently by saying, well, let x be equal to 2a. So we got sine 2a over 1 plus cos 2a equals tan a, and proceed on that basis. And you would get the same formula. You'd end up with tan a down here. Okay, here's another example of trig identity. In this case, what we want is we're starting with something that has a mixture of single angle and double angle, top and bottom. We want to end up with a function of the single angle. So that suggests we should use, we should replace the double angles using the double angle formula with the single angle equivalence, right? So we replace the sine 2x with the 2 sine x cosine x, and replace the cos 2x. Now, remember, there are various ways of expressing the cos of 2a. We would like to have all sines on the top and all cosines on the bottom in order to have a chance of ending up with a tan. So we use the version of cos 2x that only has cosines in it. Going back to the log tables here, this is the cos of 2a. This one isn't suitable, but if you replace the sine by 1 minus cos squared, you get this version of it, which is has a cosine only in it. Okay, and you proceed there, simplify it, the ones cancel out. You get 3 sine x plus 2 sine cos x on the top. Now the hint is that you're looking for tan x. So if you take out a sine x on top and a cosine x on bottom, it factorizes nicely, and the second factor cancels. So you end up with tan x as required. Now let's look at an exam question that has one of these trig identities in it. And this is actually a relatively tricky one, because if you look at this at first glance, you're looking for a compound angle result, with the compound angle being 3a, but you're starting off with a 7a, and you wonder how to get there. You probably need to think about this for a little while, but to get from a 7a and an a to a 3a, the only way you can really do that, if you look through what's available in the log tables, the only one that looks like it might get you there is one of these formulae, where you have an a plus b over 2 and an a minus b over 2. if you subtract two angles and divide by 2, if you look at the actual problem, subtracting 7a minus a and dividing by 2 would get you to 3a. So that looks kind of promising. So you want to use one of the formulas that has the same format, a cosine plus a cosine on top, but it has the a minus b over 2. So this equation looks promising. And underneath the line, again, you want to get 3a in the result. So you have the sine and you have the 7a and the a here. So again, you'd like to be able to subtract. So it looks like you want the sum of cosines and the difference in sines. Right? So this formula and this formula are the ones you should use. But using, instead of a here, using 7a, and instead of b here, using a. Right, so that's the strategy. So use that formula from your log tables, the sum of cosines, replacing a and b with 7a and a respectively. And you end up with using the formula, use this formula and this formula, making those substitutions. You end up with cos 4a cos 3a and 2 cos 4a sine 3a. And fortunately, the 4a's cancel, leaving you with just the 3a's, which is what you were looking for. And note that cosine over sine is the inverse of sine over cosine. So it's the inverse of the tan, which is called the cotan of 3a. Okay, so that was quite a tricky one. You did need to use these unusual formulas and log tables to get there. But this was an exam question, so you actually do need to be able to work through these trig identities using the available formulae in the log tables. Okay, let's look at a couple of more exam questions. This one is a bit more straightforward. Here they're telling you that the cosine of 2 theta is 1 over 9, and you want to find the cosine of theta. This is clearly use the double angle formula because you want to express cosine of 2 theta in terms of cosine of theta. Again, there are multiple ways of doing the cosine of 2a, but you want to express it just in terms of cosine of a. So you use this version, which you can derive from what's in the log tables very quickly, using the fact that sine squared plus cosine squared is equal to 1. And you find cosine 2a can be expressed in terms of cosine of a. And then just replacing a with theta and replacing the cos 2 theta with 1 over 9. You find you have an equation in cos squared theta. And then it's just simple arithmetic to work out what cosine squared theta is. Eventually it's 5 over 9. You take the square root, but there are two possible values. There's the plus and minus values of the square root. Both of them, when squared, will give you 5 over 9. And you can simplify it slightly. They ask you to put it in the form of the square root of a over b, where a and b are both integers. So you can observe that the square root of 9 is 3. So you can take 1 over 9 out of the square root in the form of 1 over 3. And you still have the square root of 5. Okay, so you're not quite finished when you get here. You always note what the particular form that they're looking for the answer in. So you need to go one step further to express it in that form. Okay, let's look at another exam question. And this is for an inverse trig function, effectively. You're looking for values of x for which cos 2x equals -1 minus root 3 over 2. This is effectively looking for the inverse cosine of minus root 3 over 2. But there's an extra step there because that'll give you double the angle you're looking for. And note that they ask for all of the values, but in a particular range of x. Okay, so you can use your calculator if you like and see that the inverse cosine of minus root 3 over 2 is 150 degrees. But that's not the only solution. If you look at the unit circle, there's a second angle at 210 degrees, which has the same cosine. Right, so if we plot the cosine here and look at the value minus root 3 over 2, see where our cosine function intersects root 3 over 2, we see that as expected, it intersects it at 150 degrees, but it intersects it again at 210 degrees. However, this is a periodic function, so it happens again at 510 degrees and 570 degrees, and it'll happen again, another 360 degrees later. Now, how far do we need to look? Well, we're told that x is between 0 and 360 degrees, which means that 2x is between 0 and 720 degrees. So we need to look over the range of 0 to 720 degrees, which is what I've drawn here. And we see that there are 4 points where this happens. There's the expected values of 150 and 210, but there are 2 more values at 510 and 570. Okay, so those are the four answers for 2x. But they want you to find the values of x. So just divide these angles by 2. We get 75, 105, 255, and 285. Now, if you want a slightly more formal way of doing that, what you would say is, okay, there's a solution, 2x equals 150, but you can always add any number of 360s to that. There's a second solution at 210, so 2x equals 210, plus any integer multiple of 360 added to that. And then divide that by each of those by 2 to get x equals 75 plus a multiple of 180, or x equals 105 plus a multiple of 180. And those values then are, well, 75 plus 180, 75 plus twice 180, and so on. Similarly, there's 105 plus 180, 105 plus twice 180, and so on. But we're told to find only values of x between 0 and 360. So by inspection, we see these first 2 are between 0 and 360, and these first 2 are between 0 and 360. So these are the 4 answers you select. So, I mean, either way will give you the same 4 answers. Okay. Let's look at another exam question. This is actually quite a tricky one. When I looked at this, I didn't see an obvious way of doing this. Well, that's not quite true. If you look at the sample answers in the marking scheme, which you can see online, there's a very simple and elegant solution for this, which I didn't spot when I looked at this question. And in the heat of an exam, I probably wouldn't have spotted it. So I used a brute force approach, a direct brute force approach to solve this, which is perfectly valid. If you did spot the simple way of doing it, then well, kudos. But I'm going to show you the brute force approach. You can look online and see the shorter, more elegant approach if you like. So the brute force approach is, well, we want to write sine 2a in terms of y, but y is effectively twice cos a. So we want to express sine 2a in terms of cos a. And how do you do that? Well, first of all, you can express cos 2a in terms of cos a using the double angle formula as before. But how do you express sine 2a in terms of that? Well, to convert between a sine and a cosine, you use the fact that sine squared plus cosine squared equals 1. So the sine squared of 2a is 1 minus cos squared of 2a. And now you can use this formula for cos 2a in terms of cos a. So replace the cos squared 2a by this double angle formula, and replace then the cos of a by y over 2. And from then on, you've just it's just a little bit of algebraic manipulation to rearrange this as a function of y, and you end up with the sine squared of 2a is 1/4 of y squared times 4 minus y squared. Now, you want to take the square root of that to get sine of 2a, which is what you were looking for originally. You might ask, why not write plus or minus this square root, which you would generally do to solve an equation like that? And the answer is because you're told that a is between 0 and 90, which means that 2a is between 0 and 180 degrees, which means that the sine of 2a is positive. So you only need the positive square root. You can simplify this slightly if you want by noting that, you know, 1/4 y squared, you can take that out of the square root and say 1/2 y. But you need to leave the 4 minus y squared inside the square root. So it's a bit, as I say, this is a brute force approach. There is a more elegant solution if you spot it. Okay, here is another, well, it's a relatively simple trig identity. It's another one of these cos 2a double angle formulas. As I said, there are about 4 different ways of expressing cos 2a. They ask you to show this one. Well, you're entitled to start with the formula that's in the log tables, which is cos squared minus sine squared. You want to get rid of the cos squared to get it in this format. So use the fact that cos squared plus sine squared equals 1. You can replace cos squared by 1 minus sine squared. And this gives you the desired result. Okay, so that was a nice, easy few marks in 2019. But there was a trickier part B to that question. Again, when I looked at this at first glance, it looked like a difficult question. How do you find this interior angle in where the diagonals of a cube in Sept? These are the internal diagonals of a cube. So it's a 3-dimensional problem. It looks a bit tricky, but it turns out to be a fairly simple question when you break it down. So the way I chose to do it was, let's call the size of the cube the edge lengths x, and we'd like to work out the length of these diagonals. And then note that because of symmetry, they meet at half the length of the diagonal. So you can form this triangle that they've shown you originally in the question. This triangle, we'd like to if we can work out the length of the three sides of this triangle here, we can use the cosine rule to work out the cosine of this angle. So that's the strategy. Let's work out the length of the three sides. Well, one of them is just the edge of the cube, so it's a length x. We need the length y, which is half the length of this diagonal. How do we get the length of this diagonal? Well, first we look at the face diagonal and apply Pythagoras. This is a square on top here. So this face diagonal D has a length of, well, its square length is 2x squared. And then we apply Pythagoras to this triangle here that has the internal diagonal y in it. It has this other edge length x, and it has the third side of the triangle is d. So apply Pythagoras to that. We get this length squared is equal to d squared plus x squared. But d squared we already worked out as 2x squared, and that gives us 3x squared for the length squared. So the length is root 3x. That's the length of the full diagonal. We want half the diagonal, so it's that divided by 2. Okay, so now we have the length here, the length here, and the length here. Just apply the cosine rule here. We have x squared. So we got this length squared is equal to this length squared plus this length by this length times the cosine between them. All right, so x squared is y squared plus y squared minus 2y squared times the cosine of this angle theta. We know what y is in terms of x, so make that substitution. Y squared, in fact, is 3/4 of x squared when we square this. And now we see we've got x squared everywhere. So we can divide across by x squared. And we're just left with some numbers and the cosine of theta. So we just need to reorganize these numbers. Add a 3/4 plus 3/4 to get 3/2, in fact. Well, actually, in this case, it's simpler to multiply by 4/3 first. And that gives us a 1 and a 1 and a 4/3 here. Add those, subtract 4/3, we get 2/3, and divide by 2. We find cosine of theta is 1/3. They don't ask you to work out what theta is. Just find the cosine of it. So you're done when you get this far. Okay, so it looked like a tricky question in the end, but it turned out to be just Pythagoras' theorem on the cube and the cosine rule on this little triangle here. Right. Okay, so those were a few typical exam questions. And I think we're done. Unless anybody has any questions that they want to run through Eamon there.
Thank you again very much to Ed and Frank for a great presentation and lots of questions solved. And hopefully we'll see you again next week for the geometry of the line tutorial. Bye for now.